Dear viewers of this TCE Learn Easy or Made Easy program, welcome back and thank you for your support by subscribing the channel and making it reach many concrete engineers. In this video, let us see the step-by-step procedure of analyzing a continuous beam by slope deflection method. So this slope deflection method will be included in the structural analysis syllabus of many universities. So hope you would find that helpful. So let us take an example of a two-span continuous beam. Span ABC. Span AB is 10 meters and BC is 6 meters. AB is subjected to a UDL of 12 kilonewton per meter and BC is subjected to a central point load of 160 kilonewton. The moment of inertia of span AB is 2I and moment of inertia of span BC is I. So the first step by slope deflection method is identifying the unknown rotations and forming the equations of equilibrium. So to do this, to identify the unknown rotations, a simple thumb rule will be see whether there are any fixed support in the continuous beam. Say in this beam, support A is fixed. So we know that a fixed support will not, or there will be no rotation, there will not be any rotation in a fixed support. And hinged support, it will rotate as well. This hinged support or free support will rotate. So identify the fixed support. So here support A is fixed, therefore theta A is 0. Hence, theta B and theta C are the two unknown rotations. So this is the first step. You need to identify the unknown rotations. In case if A is also on roller or pinned support, then theta A, theta B and theta C will be the three unknown rotations. So here two unknown rotations. So if there are two unknown rotations, we will be requiring two equations of equilibrium. Okay? So to form the equations of equilibrium, the thumb rule is leave the fixed support. Leave the fixed support. At all other supports, sum of moments should be equal to 0 for equilibrium. So if we take B, the end moment this side will be MBA and end moment this side will be MBC. So MBA plus MBC equal to 0 is the first equation of equilibrium. And at support C, sum of moments. So only one moment, end moment MCB is there. So MCB equal to 0. So the first step is identifying the unknown rotations and forming the equations of equilibrium. Step 2, forming the fixed end moments. So we should treat every span as a fixed beam and form the end moments, and we call this as fixed end moments. And this fixed end moment is purely formula. So it depends on the type of applied load. So in case if we have UDL, the end moment, fixed end moment at left hand will be minus WL squared by 12 and at the right hand it will be plus WL squared by 12. If it is a central point load, at left hand minus WL by 8 and at the right hand it will be plus WL by 8. For various loadings, we have different fixed end moment formula. So span AB is subjected to UDL. The fixed end moment formula is minus WL squared by 12 and plus WL squared by 12. Therefore, we'll be getting minus 100 kilonewton meter and plus 100 kilonewton meter. In the span BC, it is central point load. So minus WL by 8 on the left and plus WL by 8 on the right. So we get minus 120 kilonewton meter and plus 120 kilonewton meter. Then step 3, forming the slope deflection equation. So the slope deflection equation need to be formed for every span. So for every span, say for span AB, we'll be having two end moments, MAB and MBA. For span BC, we'll be having two end moments, MBC and MCB. So a slope deflection equation is the equation expressing the end moments in terms of the fixed end moments and in terms of the end rotations. So a typical slope deflection equation would be MAB for span AB, MAB will be equal to M of AB plus 2 EI by L 2 times theta A plus 1 time theta B. That is 2 times theta of the near end plus 1 time theta of the far end. For AB, A is the near end, B is the far end. So MFAB we have calculated the previous step, minus 100 plus 2E into moment of inertia for span AB is 2I. So substitute 2I divided by L, L is 10 meters, 2 theta A plus theta B. So it will result in with minus 100 plus 0.8 EA theta A plus 0.4 EA theta B. And since EA theta A equal to 0, we can ignore it and therefore we will be getting minus 100 plus 0.4 EA theta B. Then in span AB we have MBA. So MBA equal to M of BA plus 2 EA by L, 2 theta B plus theta A. So M of BA we have calculated 100 plus 2E into I is 2I divided by L. That is 10 meters into 2 theta because theta A is 0. That will get 100 plus 0.8 EI theta B. Similarly, in span BC, MBC equal to M of BC, that is fixed moment, plus 2 EI by L into 2 times theta B. Near end is B now. In BC, near end is B and far end is C. So 2 theta B plus theta C. Here, nothing will get cancelled because we have theta B as well, theta C will exist. So you'll be getting minus 120 plus 0.67 EA theta B plus 0.33 EA theta C. And MCB will be equal to M of CB plus 2 EA by L to theta C plus theta B. So in CB, C is the near end, B is the far end. So 2 times theta near end plus 1 time theta far end. So 120 plus 2 EA by L, 2 theta C plus theta B. So this equation you'll be getting. Then step 4, solving for unknown rotations. So this, you go back to step 1 where we have the equations of equilibrium. So we have MBA plus MBC equal to 0 and MCB equal to 0. So in the third step, we have all the end moments expressed in terms of fixed end moments and end rotations. So we can substitute here the equation of equilibrium. That is the first equation of equilibrium is MBA plus MBC equal to 0. MBA equation we have, MBC equation you have equal to 0 and you resulted with the equation. And then using equation 2, that is MCB equal to 0, will result in another equation. Solving these two equations, we get the value of EA theta B and EA theta C. And substituting these values in the fixed end moment or in the slope deflection equations, we'll be getting the final end moments. So MAB we have already arrived in the slope deflection equations minus 100 plus 0.4 EA theta B. So EA theta B we have here, substitute, we'll get. And MBA will be 100 plus 0.8 EA theta B. So we substitute and get. Similarly, MBC and MCB equal to 0. With this, we will have completed the shear force diagram and bending moment diagram. So let us see first how to draw the shear force diagram. So to draw the shear force diagram, first mark the end moments here. To mark the end moments. So we have MAB minus 75.8, MBA say 148.4, let us make it as 148.4, and MBC minus 148.4, and here MCB 0. We can very well check the value. Say in case of continuous beam, this is fixed support, so you should definitely get a negative bending moment at the support, and at B moment should get balance, so we got balance, and this is the freely supported end, so it should get 0. So these are the end moments. So consider span AB. To take span AB here, span AB. So the span AB substitute to UDL, and since it is minus 75.8, mark it as anti-clockwise. Here plus 148, so mark clockwise. Now we need to find the reactions RA and RB1. So using sigma V equal to 0. To find reactions, we will be normally using the static equations of equilibrium, sigma V equal to 0 and sigma M equal to 0. So using sigma V equal to 0 upward positive, we will be getting RA plus RB1 minus 12 into 10 equal to 0, or RA plus RB1 equal to 120 kilonewton. Then taking moments about A, we already have a moment, so this is anti-clockwise, so minus 75.8 plus 12 into 10 into 5 plus 148.4. This moment is there, minus RB1 into 10 meters equal to 0. Therefore, you can find RB1 and RA. In a similar way, mark the free body diagram of span BC, mark the reactions. So here we have end moment of anti-clockwise moment of 148.4. So using sigma V equal to 0 and sigma M equal to 0 and take, we will be getting the reactions RB2 and RC. So here you form the total reaction. Say RA we have, RB comprises RB1 and RB2, RC we have. So with this we can draw the shear force diagram. So the shear force diagram we can quickly go through from left to right by following this procedure. Say at A, you need to consider two positions that is clearly notified as P1 and P2. So P1 means position 1 and P2 means position 2. Position 1 means standing at A itself and viewing to the left side. So you stand at A and view to the left, there is no load, therefore 0. And position 2 means you just stand, you stand just to the right of A. So we are standing here and we view to the left side. So if you view to the left side, we have left up force. So according to shear force sign convention, you follow the shear force sign convention. Left up positive, left down negative, right up negative, and right up positive. So left up is positive, therefore plus 52.74. Then come to B point. So at B point we have two positions. Position 1 means stand at B itself and view to the left side. P2 means position 2, that is stand just to the right of B and view to the left. So if you stand at B itself, then earlier we have 52.74, that will come into play. Then we have this UDL left down is negative, so minus 12 into 10, if minus 67.26 will be the shear force. And when you go to position 2, that is if you stand here, this reaction will be getting added, that is left up. So minus 67.26 we have, then plus 172, therefore 104.73 is the shear force value here. Then go to point D, P1, stand here and view to the left, therefore you'll be having this value as such, not 4.73 to come. And then position 2, that is just to the right of D, you stand and see to the left, this load will come into play. Therefore, this is left down. If I stand here and see to the left, I have a left downward load, so minus 160. Therefore, minus 55.27. And go to position 1 of C, that is stand at C itself and view to the left. So we can simply transfer this value 55.27. And then if you go to the position 2, that is if I stand here, this 55.27 minus 50, because left up is minus. So here actually, sorry, you have minus 55.27, minus 50.2 plus left up is plus. So plus 55.27 equal to 0. So when we plot these values at the points, say at every point we have two values, simply plot the values. At A we have 0 and 52.74. At B we have minus 67.26 and plus 104.73. At D we have 104.73 and minus 55.27. And at C we have minus 0. So this will automatically will take you to the shear force diagram. Then to draw the bending moment diagram, say we have the reactions RA, RB1 and all. So this will help finding the maximum bending moment. So to find the maximum, we very well know that where shear force is 0, bending moment will be maximum. So if you consider span AB, shear force at XX will be equal to left up 52.74 minus this 12 into X equal to 0. Therefore, X will get a 4.4 meter. At 4.5 meter, the bending moment will be maximum positive bending will be there. So MXX equal to this 52.74 into X, left clockwise positive. This is left anti-clockwise, so minus 75.8. And this UDL will also produce anti-clockwise moment. So left anti-clockwise minus 12 into X by 2. So maximum bending moment will be 40 kilonewton meter. That will be, we call it as O1 ordinate. In the diagram, I will show what is O1 and O2. Similarly, consider span BC. In case of UDL, maximum positive bending moment will occur under the point load. So if I find MD, this MD will be equal to either RC into this distance or RB2 into this distance minus 148.4. So 104.73 into 3 minus 148. So that will be the value of maximum positive bending moment at D. So to plot the bending moment diagram, how to plot the bending moment diagram? So the procedure is, first you plot the free BMD. Say span AB is subject to UDL. So draw parabolic curve here first. This should be drawn first. And then in case of, this is central point load, so that triangle should be drawn first. And then we should mark the end moments. So here end moment we have got minus 75.8, that is anti-clockwise. So to see where to plot this minus 75.8, you stand here, you place a point here, apply an anti-clockwise moment. Since it is minus 75.8, apply an anti-clockwise moment here and see whether this beam will be pushed up or down. So if I apply an anti-clockwise moment here, the beam will be pushed up. Therefore, I am marking 75.8 at the top. Then come here. Here we have two values. One is 148.4 and here minus 148.4. So you keep point at pen at here and then apply a clockwise movement. So this clockwise movement will make the beam move up. Therefore, we need to mark it upward. Similarly, this side we have anti-clockwise movement. So apply an anti-clockwise movement. So the beam will again move up. So this point is got. Here we have 0. So connect these points. So shade the rest. So this will give the net bending moment diagram. And this value is O1 and this value is O2. This we have already found. So this completes the analysis of a two-span continuous beam by slope deflection method and drawing the shear force diagram and bending moment diagram. Please subscribe our channel and join the mission of nation building with concrete concepts through Learn Easy program. Thank you.